The ones I wrote down. Let's record.
I like the guys asking on the street, why live? I want to be. I said, why live? Are you recording? Are you recording?
I'm recording now, yeah. I just started.
Okay.
All right, so I'm gonna work my way through these. If I'm being honest, I didn't do them, so you can kind of see how I work through them. So number one, go ahead and draw it out. That look like what y'all got? Find resistance total. All right, so the first thing you do when you have, what type of circuit is this?
Series parallel.
Series parallel, so I have both of them. So the first thing you do to find resistance total of a series parallel circuit is you break down the parallel circuit, right? So this right here is my parallel circuit. I have any that start at the same point and end at the same point are going to be the same circuit. So I have technically how you would read this, like if this is a word problem, it would be R2 and R3 are in series with each other, right? So R2 and R3 are in series with each other and in parallel with the combination of R4 and R5, which are in series with each other. Does that make sense? Because those are, so in order to reduce this down, I am going to combine my series loads inside my parallel loads. So I add 20 and 50 together, and I add 35 and 40 together. Make sense? So that that gives me 70 on the top side. So let me see if I can. And 75 on the bottom. So that gives me equivalent resistors. Is this how I do this? Nope. Don't do that. Nope. I don't know how to do that. There we go. So, I'm just going to draw in red. So inside of this, I would have a resistor here and one resistor here. Does that make sense to everybody? So I combine these. So this, I'm going to call this R23 equivalent resistor, which is going to be 70 ohms. And then R45, which will be 75 ohms. Everybody good with that? Now I have two resistors in parallel, which are in series with R1, 6, and 7. So now what do I do?
Then you have to do different parallel equation, right?
I gotta do the parallel equation. So there's two different equations that I can do with this one. I'm gonna work through both of them. So the first one, the equation that always works is so resistance total is equal to 1 over R1 plus 1 over R, your second resistor. So plug my numbers in, 1 over 70 plus 1 over 75. Unless you're really good at figuring out what your least common denominator is, I would recommend putting this into decimal. Does that make sense? So get out your calculator. Can somebody give me what 1 divided by 70 is?
0.014.
14. What's 1 over 75?
0.013.
Does everybody see how I got there? You want to go out probably at least to your thousands place, so at least 3 out. So I add those up and I get 1 over 0.027. And then somebody do that math for me. What's 1 divided by 0.027? 37.
37.03.
37.03. You're good with that? So that's ohms. So another rule to follow whenever you're doing parallel resistances, whenever I'm combining 70 and 75, your resistance total is always going to be less than your smallest resistor. So it's always going to be less than 70. So if you come up with an answer that's 75, 80, something like that, it's not correct. When you're doing parallel. So now essentially what I did was I broke this down even further and I created one resistor inside of here that is the combination of all of them, and it's going to be R2 through 5 at 37.03 ohms. Everybody go over that? So I just kind of kept breaking it down. So what kind of circuit do I have now? Series circuit. How do I find the resistance of a series circuit?
You add them up.
Add them up. So resistance total is equal to R1 plus R2 through 5 plus R6 plus R7. So I've got 5 plus 33.03 plus 10 plus 17. So may do 27, 32, 65.03. Everybody follow me how I got there?
Yeah, I had that one correct.
Good. 65.03. Any questions on this one?
It's like you say, that has to be less than the answer for what that you say has to be.
I'll show you. Let me show you on the next one.
Ah.
I'm trying to do these as big as I can so I know, so they can kind of be seen from. Then I said find current total.
This is.
What's that?
This is the series equation, right?
Are these in series or parallel? Parallel.
So you add these up.
Nope. Series you add them up. Parallel you have to do the equation.
Yeah, that's what
But I'm looking for current total, right? What's my equation for current? according to Ohm's law.
35.
Close.
E times R or something.
5, 24.
E divided by R.
E divided by R. Have y'all heard of the, like the Ohm's law triangle?
Oh, yeah, it's around one.
Yeah.
So I re-
You go on
Right.
the side and
Like
then-
I recommend everybody having an Uglies book. Like it has all the equations you need for electrical on the front page, plus a lot of other stuff. I think they're about $10-12 on Amazon or something like that. I'd recommend getting one of those. Ohm's law is E, I, and R. So the triangle works like this. If you have any of the two, you can find the third one. So if I'm looking for I cover it up and it's E over R. If I have R, it's E over I. If I'm looking for E, it's I times R. That makes sense? Kind of a simple little way of thinking about that. So
The I, looking the E will be I times R.
if I'm looking for E, it would be I times R.
Oh, okay.
So now I have to say which voltage am I using? So in a series circuit, my voltages are different, right? My voltage drops across each load. This is a parallel circuit, which means that what? Voltage is the same at every load. So your house is wired in parallel, right? Because you have, what's your voltage at every plug? 120 volt, you have 120 volts at every plug. Everything's wired in parallel. If you didn't, like you have goofy voltages around your house. The amperages are what are different. So I'm going to use for I total, I'm going to use voltage total, right?
120.
Which is 120. What resistance am I going to use to find I total?
Do you use each one or do you add one?
You'd add them up, which would be what?
35.
No, you don't add them up like that. But you would add them in parallel, which would give you your resistance total, right?
Oh, all right. Yeah.
So do I have either one of these? Both.
Well, you have the voltage.
I have the voltage, so I'll write that in 120. I don't have resistance total, but I can find that. Resistance total. What's my equation for a parallel circuit for resistance total? Good. Everybody following that? I'm gonna do this. I didn't do the other one in fractional form. I just did decimals. But I didn't do the other.
R1 times R2.
Yeah, I'll go back and do that one in a second. I just forgot. So this one, what's going to be the easiest way of doing that one? Least common denominator.
Yeah.
Yeah,
Right. So what's my least common denominator for 5, 10, and 20?
4
It's what?
for the 20.
20.
4.
20. Everything goes into 20 right there. So 5 goes into 20 how many times?
4.
There you go. 4 over 20. 10 goes into 20. And 20 goes into 20 one time. 4 plus 2 plus 1. 1 over 7 over 20. So this is where some people get confused, but because of the reciprocal law, I can take this, flip it upside down, and get rid of the numerator and say this is 20 over 7. So 20 over 7. What's that? 2.9 something? 2.8?
2.85.
2.85. And that's my resistance total, right? So 2.85 ohms. So what's 120 divided by 2.85? 50, 49?
42. 10.
42.1? Current is measured in what? Amps. So that is your current total for that circuit. Everybody go with that? Going back, I forgot that I could do this. So I found resistance total this way, finding two resistors. You have another equation for two resistors, which makes it a little bit easy. You can use resistance total is equal to R1 times R2 over R1 plus R2, and then plug in 70 and 75 from the top and bottom and figure, and it'll give you the same answer. So that's just a little bit easier way of doing it, because you don't have to find decimals and you don't have to find common denominator. But you can only do that when you have two resistors. Good. Last problem. You say you got something different?
Yes, 36.2.
So that has to be, I mean, that's close, 36.2. This is like, you're gonna have rounding errors right here. So this way is actually a little bit more accurate, because you're gonna have to round a number to thousands, which is gonna change your answer and stuff like that. So this would actually give you closer to the correct answer.
Oh.
40 ohms, 20 ohms, 40 ohms. And I wanted you to find E1.
You just divide by.
So well, the first thing I want to do is figure out what I want to find. So I want to find what is in a series circuit, what is the same at every load? The current, not necessarily milliamps, the current. So my current here is the same as my current here, is the same as my current here, is the same as my current here. What's different at every one?
That resistance?
Well, the resistance is different, but based on that, what's the voltage? You're going to have a voltage drop across every one. So I'll have a voltage 1 here, voltage 2 here, and voltage 3 here, right? So voltage is based on the resistor size. So if my current is the same at every one, and here, my current at every one is my current total. Everybody go with that? So if I'm wanting to find E1, what's my equation for voltage? I times R. So I'm finding E1, so I have I times R. If I'm wanting to find what current am I going to use to find my voltage at E1?
0.004.
Nope, I didn't give you a current. Like what, like symbol wise, what current am I going to use?
Yeah.
Amps. I'm going to use current total. That's what I'm looking for. Current total. Does that make sense? So current total, which resistance am I going to use?
Resistance to it.
Nope. Because I'm
one for E1.
resistance for ones, because I'm only looking at this one.
Okay, E1. Yeah. Right.
So R1. So do I have both of those?
You have resistance and you have current.
I don't have current. I didn't give you a current. Right? But I can find current. What's my equation for I total?
Divided by R.
Which E am I using? 100, right? So this can be represented by voltage total. Other times it can be EA for applied voltage. It can be either one, but I'm going to use, for current total, I'm going to use voltage total over which resistance?
15. Or resistor 1.
If I'm finding the total current.
Oh, so the total.
Total current's going to use which resistance? If I'm using,
Add them up.
which is called what? Resistance total, right? Do I have my voltage total?
If we add all of them.
Just the voltage
So
total.
the voltage is the same, so it's 100.
Voltage is 100
The 100.
for my voltage total. Do I have resistance total?
No, not yet.
No, but you can find it, right? Resistance total. How do I find that for a series circuit? Add them up. So R1 plus R2 plus R3, 15, 20, and 40. 15 plus 20 plus 40, which gives me 75. Everybody go with that? So I can plug in 75 here. 100 divided by 75, 1.25, right? No, 1.33.
Yeah.
1.33. 1.33 repeating. Current is measured in what? Amps. So that's my current total. Now I work my way back up here and I say 1.33 times 15. And what does that give me?
$19.96.
19.96. E is represented in what? Volts.
That's the volts.
Voltage. So that's my voltage at 1. Is everybody good with that? If I wanted to find E2, what's my equation for E2?
E2 equals ITR2.
Yep. So do I have IT? Already found that, right? 1.33. Resistor 2 is 20. Somebody do that math for me.
26.6.
26.6 volts. E3, current total times R3. 1.33 times 40 is 53.2. I don't think have we talked about Kirchhoff's laws yet? Kirchhoff's voltage laws for series circuits says that we will drop all of our voltage through a series circuit, right? So if I have E1 is what? 19.96 plus 26.6 plus 53.2. Somebody do that math right quick.
$99.76.
99.76. So due to rounding errors, we didn't get there, but it should add up to our voltage source. Does that make sense? So we will drop out, technically, all of our voltage across the series circuit will add up to 0, because technically this is a negative voltage, because you're dropping it as you go, and it will add up to 100 volts. Does that make sense? Good. All right, let's go over section. You'll do section 1 review.
I think we tried to do it in class, huh?
Did I go through section 1 review in class?
I think so.
I think so.
Yeah.
I think I had an answer to it.
Number 1 is B, 2D, 3A. Yeah, we did that in class. All right. I don't want y'all to worry too much about this, but like that will be a couple of questions on the test will be finding something like that. I always, just so y'all know, I try to make it harder in class than it is on the test. So I'd rather this be hard now than be hard whenever you're taking the test. I don't want anything to kind of surprise you when you're taking a test. So let's move on to section 2. they're going to get into the specifics of how alternating current and direct current work. And I'm going to talk about the sine waves and stuff like that, but I'm not going to dig into it too much just because, like, I had to learn this stuff in college and I never used it. I never used like the figuring out what a sine, like different parts of the sine wave. Like that never came into, it never was an issue whenever I was an industrial electrician or instrumentation person. But it is good to know for troubleshooting purposes, like how stuff works or how a generator works. That is good to know. And we're going to talk about apparent or power factor. So some of those trade terms on page 14 are good to know. The ones for power factor are apparent power, reactive power, and true power. I'll talk what those are, a little bit important to know, but you should know what y'all know what frequency United States runs on?
No.
60 hertz. Pretty much everything runs on 60 hertz, and then they use a variable frequency drive to change that for motors and stuff to change the speeds. Frequency is measured in hertz, that's on there. Power factor, RMS voltage. RMS voltage is technically what we read, root mean squared. But that's like our 120 volts is not our peak voltage. That's our root mean square voltage. Probably doesn't mean a whole lot to y'all. But 210, my first highlight is the second sentence of 210. One complete waveform or cycle includes a complete set of variations with two alternations in polarity. So one waveform has two alternations. So if you're looking at the board, this is one waveform. That's one sine waveform. You have one alteration in the positive and then one alteration in the negative. Good? Page 15, that third paragraph on page 15. I'm gonna read you my highlight and then I'm gonna talk through it. Third paragraph on 15, third sentence. I think it's just one long run-on sentence. Because voltage is proportional to the sine of the angle. As the conductor loop goes 360 degrees around the circle, the voltage will increase from 0 to its maximum positive value at 90 degrees of rotation, back to 0 at 180 degrees, down to its maximum negative value at 270, back up to 0 at 360 degrees as shown in figure 23. So it says that it's going to go 360 degrees, right? So if I have a sine wave that goes like this, and they talk about 360 degrees, all this is, like if I cut this off, this bottom part off, and moved it over here, what do I have? I have a circle. So if I have a circle and I cut it into 4 quadrants, and I'm saying this is 0 degrees. 0 degrees. This is going to be 90 degrees. This is going to be 180. See how 180 is flat? So this is 90, 180, 270, 360, or back to 0. That's 0 and 360, right? So 180, 270, 360, or back to 0. Does that make sense? So as this is literally what a sine wave does, or this is what AC electricity does. So whenever they say 90, reading through this, the conductor will go 360 degrees around the circle. The voltage will increase from 0 to its maximum positive value at 90 degrees, back to 0 at 180, to its maximum negative at 270, and back to 0. Does that make sense? That's pretty much as far as I want to take that. And you can see, like, so how a generator for like your house works is by cutting magnetic lines of flux with a coil. So you can see like this would be like the rotor that turns inside the generator. So you can see this rotate, and as it's rotating, you can see what the sine wave's doing. And you can read through that if you want, but I'm not that concerned with y'all knowing that. If you know what I just said here, that's sufficient for your knowledge for this class. Page 16. We want to AC terminology with sine waves. I have that whole first paragraph on page 16 highlighted. So the frequency of a waveform is the number of times per second identical pattern repeats itself. Each time the waveform changes from 0 to a peak value and back to 0 is called an alteration. 2 alternations form 1 cycle. The number of cycles per second is frequency. The unit of frequency is hertz. 1 hertz equals 1 cycle per second. What did I say the frequency in the United States is?
60.
60. So you have 60 sine waves per second in AC. So whenever, like your incandescent light bulbs at your house, they are constantly going from positive to negative all the time. But it's happening 120 times a second because it'll give you positive voltage and then negative voltage for each waveform, and that happens 60 times a second. So it's so fast that we can't even see it. But if you took an incandescent light bulb and you put it in a slow, what's that called? Slow-mo camera or whatever, and you slowed it way down, you could actually see that light like pulsing, turning on and off as the fluctuations go through. But it happens so fast our eyes can't keep up with that, and all we see is light. Make sense? The equation right there, T equals 1 over F, so that's time equals 1 over frequency. You're going to use that equation on the practice test. You're going to have to switch it around for frequency, but frequency is going to equal 1 over T. So you can highlight the T equals 1 over F, but out to the side I would write F equals 1 over T, because they're just going to give you a number of cycles and seconds and have you find frequency. On the right-hand side of page 16, that the big paragraph where you see the blue highlighted peak voltage, I started on that second sentence where it says, for example, and I highlighted 3 sentences. For example, specifying that a sine wave has a peak voltage of 170 applies to either the positive or negative peak. To include both peak amplitudes, the peak-to-peak value may be specified. In the above example, the peak-to-peak value is 340 volts, which is double the peak value of 170 because the positive and negative peaks are symmetrical. So what that's saying is my sine wave right here, they're saying if I had my maximum positive was 170 volts and my maximum negative was 170 volts, that is my peak voltage, right? And then they want you to know that if I have from the maximum positive to the maximum negative, that's going to be 340 volts, and that's going to be your peak to peak voltage. So peak voltage, peak to peak voltage is going to include, it's not going to call this negative because this is technically a negative voltage, but not really. But it's just going to add them both together. 170 plus 170 is 340, which is your peak to peak. First sentence on page 17 is highlighted. Since the peak value of the sine is 1 and the average of sine equals 0.637, then the average values can be calculated as follows. Average values equal 0.637 times the peak value. So if you're looking on the board, like that's what your average value is right here. I've never done anything with the average value of a sine wave.
In between those lines?
It's just right, it's right there, like that's where it's found, like this is the average. Because they're taking the average of the sine of 1. Remember the voltage that I said we do use is the RMS voltage. So RMS voltage is what we see on our meter. Whenever we put our meter and a plug in the wall, we see RMS voltage. We're not seeing peak voltage or negative peak voltage, we're seeing RMS voltage. But they're gonna want you to know how to calculate average voltage. So if my peak voltage was 170, and I want to know my average voltage, I would just multiply that by 0.637. And get 108.29. 108.29. You just need to remember that 0.637 for average voltage. Average value. Skip a paragraph and then that root mean squared paragraph. I've got a sentence like a little past halfway through that paragraph in the bottom left highlighted. For a sine wave, the effective or RMS value is 0.707 times the peak value. You want to highlight that sentence. For a sine wave, the effective or RMS value is 0.707 times the peak value. So if I take 170 times 0.73, what did I say? 707? Yeah. 707, that's going to give me 120 volts. So technically, the voltage at your house or the voltage in these plugs, the maximum voltage is 170 volts. So they actually see 170 volts for just a blink, not even a blink of an eye, it's stupid fast. 120 times a second, we'll see 170 volts. But what we read on our meters is RMS voltage at 120. Good. The rest of that paragraph is an online test question. So you want to highlight that and make sure you mark that. Figure 25 shows where the effective or RMS value would fall in a sine wave. For example, with a peak value of 170, the RMS value is 170 times 0.707 or approximately 120 volts. Similarly, if you know the RMS value, you can determine the peak value by multiplying the RMS value by 1.414, for example, with an RMS of 120, peak is 120 times 1.414, approximately 170. So they're just going backwards. So you can memorize that if you want to find your peak off of your RMS value, you can multiply by 1.414, or what I'd rather you do is just remember 0.707. So if I have RMS voltage of 120 and I wanted to get my peak voltage, all I have to do is divide by 0.707 and that'll give me 170. Instead of having to memorize the 1.414. You only have to memorize one thing. You just have to remember whether you're multiplying or dividing, which way you're going. If you're getting peak voltage up, you're going to divide by a fractional number, so it's a bigger number. If you ever find peak voltage from RMS voltage and it's lower, you did it wrong. It's always got to be, peak voltage is always going to be the highest voltage. 220. AC phase relationships. I have the heading of 220 highlighted. So you're just going to need to know how, where like the phase relationships. There's not going to be a lot of stuff. If you flip over to page 18, the second paragraph on page 18, I have all of that highlighted through the first sentence of the third paragraph. So suppose the generator started its cycle at 90 degrees where the maximum voltage output is produced instead of starting at the point of zero output. The two output voltage waves will be shown in figure 26. Each is the same waveform of alternating voltage. The wave B starts at the maximum value while A starts at zero. The complete cycle of B through 360 degrees takes it back to the maximum value from which it started. these two waves are said to be 90 degrees out of phase. So if I had the same waveform, and I said this was waveform A, this is starting at 0 and ending at 360, right? 180, 270, 90. I don't know why I went in that order, but I did. And what they're saying is if you have a second waveform, so like at your house, you have two phases of electricity. You have for 220. They're not in the same phase, they're different phases, so that's how stuff works. I don't know how many degrees out of phase, but what they're saying is waveform B would start at the maximum, at 90 degrees be the negative, and then 180 be the maximum negative, 270 be back to 0, and then by the time it gets to 360, it would be back to the maximum. And they are said to be, like if I look here, from where that one started to the same point where it's here, they are 90 degrees out of phase. Does that make sense? They're just 90 degrees. So this one would be, pretty sure it'd be waveform B would lead waveform A by 90 degrees because it's kind of getting a head start, like it's starting at its maximum. But pretty much what I want you to know is they're 90 degrees out of phase. So whenever you're looking at that, all you do is find 2 points where they're at the same place. So you could do it at zeros. Waveform A is at 0. Whenever waveform B is at 0, what's it at? It's at 90 degrees. If it was more, if it was 180 degrees out of phase, which it never is, but then it would be completely opposite. If it was 180 degrees, it would be on the other side of the circle or completely opposite. 230, resistance in AC circuits. Or AC circuits with resistance only. Third paragraph, first sentence. In an AC circuit with only resistance, the current variations are in phase with the applied voltage as shown in figure 27. So if you're looking at the phase relationships of voltage and current, if it is a resistance only, which would be like a incandescent light bulb or something like that, resistor or heating element, those are resistance only. That my voltage and current are in phase, which is good. Like that's good for power to be in phase. The last two sentences of that paragraph are highlighted. Components that only have resistance include items such as resistors, the filaments of incandescent light bulbs, and heating elements. These circuits are referred to as purely resistive circuits. $240. Well, we can go ahead and do that one. Do y'all remember what that one's going to be?
0.637.
What voltage is that going to be? Average.
This 120?
Average voltage. Well, I'm not asking for like I don't have numbers on this. I just want to know which one it is. So that is the average voltage right there.
The next one is RMS.
The next one, so average is 0.637 times the peak. Good.
RMS, right?
That one is RMS. So RMS is 0.707 times the peak. What are these two?
That's
Your peaks,
My peaks, right? Peak value. What's that one?
peak to peak.
Peak to peak. Everybody go with those? So, inductance in AC circuits. Anybody have any idea what component would be an inductor to an AC circuit?
Like a heater, too? Like a heater?
No, a heater would be a purely resistive load. Anything like a three-phase motor. So they're usually called a three-phase inductive motor. So those would be an inductive load. Third paragraph in 240 on the right-hand side of page 19. third paragraph, second sentences are highlighted. Lower frequencies of AC require more inductance to produce the same amount of induced voltage as a higher frequency current. Out to the side of that, I wrote there proportional. So lower frequencies require more inductance, and higher frequencies of AC require more inductance to produce the same amount of induced voltage at a higher frequency. It's easier for higher frequency current to produce inductance. Page 20. A lot of this trade term stuff, I'm just going to kind of roll through. I'm not going to talk about it too much. Page 20, right above 250, that paragraph right above there, I have the first two sentences highlighted. The opposing force an inductor presents to the flow of alternating current cannot be called resistance, since it is not the result of simple opposition within a conductor. The name given to this force is inductive reactance. Key in on inductive reactance, because it is the reaction of an inductor to alternating current. Inductive reactance is what the resistance inductor plays to AC current. Capacitance. I don't have anything on 20 and 21, but if you flip over to page 22, I've got something in 251. Calculating equivalent capacitances. So you're going to have capacitors in parallel and capacitors in series, right? The first paragraph is highlighted on page 22. Connecting capacitors in parallel is the equivalent to adding their plate areas. Therefore, the total capacitance is the sum of the individual capacitances as illustrated in figure 32. So y'all know what makes up a capacitor? All a capacitor is, there's two metal plates with a dielectric in between them. However close they get, it puts off a different capacitance. So whenever capacitors are in parallel, you just add them up. So they are the direct opposite of resistors. So like this is representing the two plates of the capacitor. Since the top, this is kind of how to think about it. The top of the plates are connected, so those would just combine. The bottom of the plates are connected, so those would combine. So capacitors in parallel, you just add up. I don't have it highlighted, but capacitors in series, you have to use that equation, that 1/over equation, right? I don't know that you'll have a question on that, but just know that when adding capacitors or finding the equivalent of capacitors is the opposite of resistors, how y'all do resistors. 254 on page 23. Capacitive reactance. I have the second paragraph all the way down to where I say capacitive reactance highlighted, so all the way down to the bottom left. So increasing the frequency will also decrease the opposition offered by a capacitor. This is because the number of electrons the capacitor is capable of handling at a given voltage will change plates more often due to the frequent alterations. As a result, more electrons will pass a given point in a given time, so greater current flow. The opposition that a capacitor offers to AC is therefore inversely proportional to the frequency and capacitance. This last sentence is what I want you to key in on. This opposition is called capacitive reactance. So a capacitor in an AC circuit, its opposition is called capacitive reactance. An inductor is what? Inductive reactance. So you have inductive reactance, capacitive reactance. Both of them reactance. Inductive reactance, capacitive reactance. Power in AC circuits, 260. Y'all ever done equations for power? It's another one why I would recommend getting one of these books. Like all your power equations are right there on the front. The highlight that I have is that sentence after you see the blue highlighted true power. True power, or PT, is the product of a resistor current squared and the resistance. So PT equals I squared R. So if you want to find power in an AC circuit, you're getting I squared times R. Skip that little one sentence paragraph, and the next paragraph, that sentence where you see apparent power, I have that sentence and the one after it highlighted. The product of a source voltage and the current is called apparent power. Its unit of measure is the volt ampere, and its value is always higher than the value of true power in the same circuit. So you're going to have true power, apparent power, and reactive power. So that's what's going to make up power factor in a plant or anywhere at your house. I have a short video to watch.
My favorite analogy to explain this is to use the paper analogy. You pay for the it's slightly cost of the fun. The more we have, well, it's funny that we get every value of money. People knows a lot of value, they have lots of opinion, so we don't get the very value of money. The thing that represents our true power. That's what we are. The floating represents our power over it does actually have a use of the correlation of these chemical chemicals that can chemical reactive is on how power factor is therefore the ratio of the mutual power of true power in kilowatts per kW divided by the charge for the kilowatt kilowatt. So it's telling us how much value for money we're getting for the power we consume. We can break it up so that's the zero, and I will keep this up for the pricing is expressed as power flow. In this case, I'll draw it as a power factor as it's easy to visualize. The feeling of true power is the adjacent line. Then we have the flow, which is effective power on the opposite. There's a positive side, which is the opposite side. We have the apparent power. This is an angle from the true power. The angle is known as theta. You see, as a reactive power, the flow increases the surface in power kVA. We could then use power base triangle by what is given as just basics, so just
So that's pretty much all I wanted y'all to get from that. So the true power that you're calculating, P equals I squared R, that is your true power. So that's your beer in the glass. That's the good stuff. Your apparent power is the full glass. So the full glass is what you're paying for, right? You got to pay for beer by the glass. You don't get to just pay for the beer itself. You got to pay for the foam and everything. And then the foam is the reactive power, or it's the bad power. You have to have it, but if you add a bunch of inductive loads to a plant or something like that, you're going to get a lot of reactive power. And what that's going to do is that's going to mess up your sine waves for your voltage and your current. Like it's going to get them so far off, and it's going to create what's called dirty power. And this is not good. Like you have to filter dirty power and smooth out stuff and turn it back clean. and the power companies will actually charge you a penalty if you have so much reactive power. But plants use a lot of induction motors, right? Motors are on everything: hoist, lift, fans, blowers, pumps, everything's got motors, inductive motors on it. So you have a lot of inductive loads, so you have a lot of reactive power. What you can do to compensate for that is put in big banks of capacitors, and capacitors offset your inductive loads. So you don't have to pay that penalty because you have capacitors that will offset that inductive load. That kind of makes sense. That's as far as I'm going to take that with power factor, but power factor is pretty much just how well you are using your power or how well your power is provided to you. I don't know if I've said it before, but like as far as electricity stuff goes, this engineering mindset actually puts out some pretty good videos. Like if you all want to look on YouTube and look at some of that stuff, but like they have one on AC voltage and stuff like that. Like they're pretty good interactive videos. I gave you all the highlight for apparent power. So you've got 6 questions on page 24. See if y'all can knock those out right quick. All right.
Yeah, I'm trying to figure out why I'm pushing myself.
Where do you live? In Arabic?
Yeah.
You want me to give you a ride home? I live in Arabic. I'll give you a ride home. You got those? All right, I'm gonna work my way through these. You remember what my equation is for frequency?
It's F equals 5 divided by 0.5. 5 cycles divided by 0.5.
Not 5 cycles. So 1 period is 1 sine wave or 1 cycle. So 1 divided by time, which is 1 divided by time is 0.005 seconds, which gives me 200, right?
Yes.
Yeah, 200 hertz. So 1 is B. Number 2, sine wave A is at its peak voltage. Sine wave B is at minus peak voltage simultaneously. They're said to be out of phase by how many degrees?
To 180.
So if I have,
180, 90.
if I have two sine waves, what did it say? Wave A is at peak voltage. Wave B is at negative peak voltage. Should have done this in black. But they are directly opposite. So if I pick two places where they're at the same place, I will see how far apart they are. So if I'm looking at, this is B, this is A. So these are both at 0, but they're not at the same point, right? So if I looked at my two peaks, how far apart are those? If I have 0, 90, 180, 270, 360. So how far is that from that?
180.
180. 100. They're directly opposite, which if I'm looking at the other one, 180 is directly on the other side of the circle. Does that make sense? 180 degrees out of phase. Number 3. Which of the following are purely resistive loads?
Incandescent light bulb.
Incandescent light bulb, C. 4. The opposing force an inductor presents to the flow of AC current is called?
Inductive reactance.
Inductive reactance, A. Number 5, one capacitor of 120 microfarads and another of 88 microfarads are placed in parallel. What is the total capacitance? How do I get, what is my equation for adding capacitors in parallel? C1 plus C2. So 120 plus 88 is 208. Go with that. 3, apparent power is expressed by the term volt amp. Just so you know, a volt amp is equal to a watt. Volt amps and a volt amp and a watt are the same thing. Good. All right, we got a few. We got 10 more pages to go. Let's see if I can get you out of here by 9 o'clock. Section 3. Direct current. I have switching regulator in the trade terms highlighted. So switching regulator, a voltage regulator, circuit that uses switching techniques to maintain the output voltage of a power supply within a specified range. So what are some pieces of equipment that use DC voltage?
Yeah, we did this in part 2. Get the name of this.
And your car uses DC voltage, right? 12-volt batteries, DC. Most of your electronics use DC voltage. Like your computer has a power supply in it. That's taking AC power and converting it to DC power. Most of your stuff that's mobile, all batteries are DC. Linear power supplies. So this would be like the power supply that's in your computer. I have 2 sentences highlighted. No, just 1 sentence highlighted. In 311, the 4th sentence is highlighted in 311. Linear DC power supplies use telecommunications, computers, and other equipment. Linear DC power supplies used in telecommunications, computers, and other equipment are usually full wave rectifier or full wave bridge rectifier type. Towards the end of that paragraph, I have the second to last sentence highlighted. Following this, the pulsating DC voltage is passed through a filter network to smooth out the rippled DC to provide true DC voltage. So for a power supply, this is how a DC power supply would work. You would have AC voltage current going in. So you can see your sine wave there. Then you have a half or a full wave bridge rectifier. And pretty much all that does is that cuts all the negative power off. So you just have the top side of that sine wave, right? And then they use switching techniques in a filter network to make it a smooth DC output, which makes it direct current, which is constant current all the time. That's how you get DC current. So pretty much I just want you to know that you use a full wave bridge rectifier to get from AC to a rectified unregulated DC. And then from there, you use a filter network to get to smooth DC output.
The connection is with AC and one side, the other side.
The other side is supplying DC power. So input is AC, output is DC. So like your computer chargers, everybody has a computer charger where you have like the one end that plugs into the wall, and then you plug that into this box. It goes to, so that's converting AC to DC inside of that. So that's exactly what this is doing. And anything that uses something like that, where it's like a box, it's going from one, you can look at it and it'll say input 120 to 240 volts AC, output, like your phone charger will be like 2.1 amps or something like that. Like that's doing the same thing. You're taking AC power in and you're putting DC out, right? Nonlinear power supplies, 312. I have the sentence that splits the pages highlighted. So starting on page 25, compared with linear power supplies, switching power supplies have significant advantages in efficiency, size, and weight. So switching power supplies are more efficient, smaller, and lighter. So that's the last sentence on page 25 going into page 26. On page 26, the second full paragraph on page 26, first sentence is highlighted. The DC output voltage is regulated by varying the width of the switching pulses applied to the switching circuit, which is typically a transistor or a silicone controlled rectifier, or an SCR. The more you get into this stuff, the more you're going to hear about SCRs. SCRs are pretty much the primo way of switching power on and off. That's what a lot of variable frequency drives use. Three, two, one. So selection of a power supply. I highlighted the heading of 321, selecting a power supply, and then I highlighted the heading of code requirements. When you're selecting a power supply, you have to follow code requirements. So that's either by the NEC or the underwriters' laboratories. At least in the United States. I also have load requirements highlighted, the first sentence as an online test question. So the next bullet point, load requirements, the most critical factor in selecting a power supply is determining the load it must support. So a lot of the big thing that's come out in the last, I'd say 3 or 4 years, you know how you have some cell phones that have like the fast charger or something like that? Like it'll charge your phone a lot faster than the old chargers will. Well, what that's doing is that's taking AC in and that's outputting a higher amperage of DC is what it's doing. So if your phone is not rated to be charged super fast and you're plugging in this faster charger, you're gonna burn up your phone. That's why that's not good. That's why they changed up the plugins and stuff like that. But that's why it's super important if you're trying to figure out what power supply you need, that the load that it's supporting is what you want to go by. Frequency on page 27, I've got that highlighted. Frequency 60 hertz is fairly uniform in the United States. United States, we use 60 hertz. So it's top left of page 27. The last bullet point is going to talk about desired runtime and UPSs. The highlight that I have in the UPS is it's the first part of that last big paragraph in that bullet point. Some typical runtimes used with UPSs that supply smaller equipment are a computer workstation. For a computer workstation, it's going to last for 15 minutes. All a UPS is pretty much a backup battery. A lot of computers and stuff like that have to, the other night, I'd say 3 or 4 nights ago, did y'all get flickering power like a couple times? Some computers, like that's horrible for it, especially if they're like servers or something like that, like something that has to stay running. So they'll use what's called a UPS, which is just a big bank of batteries that as soon as it sees power shut off, it powers the computers or whatever with battery power. Till that power comes back on, then they turn back off. But they're plugged into the wall and constantly charging. So you plug it into the wall, and then the computers and all your other stuff you plug into the UPS. So if it ever loses power, it automatically turns on to keep the computers powered up for 15 minutes to get through that little blip or whatever. So it's just battery backup is all it is. I did like places will switch UPSs out for like DC batteries. You have to switch out because they go bad over time. I can't remember where I got it from, but somebody was throwing one away, and I saw that it was still good for a while. So I took it home, and all I did was plug it in the wall, and I plugged my router at the house into it. So whenever power went out, it powers the computer for 15 minutes. It powered my router for hours. So I still had internet with the power out. It's just battery backup. Power supply testing 322. Top right of page 27. Second sentence all the way in the top right of the page. Basically, the test involves locating a suitable measurement point, such as a terminal board or connector pin, where the power supply output voltage can be assessed for testing. Basically, the test involves locating a suitable measurement point, such as a terminal board or connection pin, where the power supply output voltage can be assessed for testing. So all they're saying is if you want to test voltage for a DC power supply, if it's for like a computer, you can pull that whole block or you can pull the side of the computer off, and then that back side will have output power. You should be able to see that and switch your meter to DC voltage and put that on your positive and negative, and you can see if you're getting output voltage on the other side of that. So you can test AC coming in, DC going out. If something's wrong, you can see if something's wrong with the power supply. But you just have to find where it says output voltage or something on the outside of that. See if you can knock those 2 questions out on page 28. You'll find those. Number 1, in the linear power supply, the DC output is smoothed by what?
Okay.
The filter network. That was the third Second portion it went through was the filter network. And then 2, typical UPS runtime for a computer workstation.
So
15 minutes. So keep a computer workstation up for 15 minutes. Section 4. So this is actually getting to the stuff where we kind of care about for instrumentation.
My arrow is disappearing. I don't know why. Can't turn pages. First one was this one. This one is here and this one is gone.
you want to go back?
Yeah, I can only go back. I tried to refresh it, it's not working. I don't know what happened. So I can't see both of them.
I have no idea. I don't know. What did
But you just went sideways.
I? Okay.
Yeah,
That'll. I don't know why that works, but it works.
first they were both sitting right there.
Has this crap been on the computer or this screen the whole time?
Yeah.
Yeah. Well, let me know when I do that. Get that off of there. Section 4, second sentence of section 4 is highlighted. The value of an analog signal varies proportionally with the magnitude of the change in the process. The value of an analog signal varies proportionally with the magnitude of the change in the process. Out to the side of that right, analog signal varies with time. On that process control train out there, I've got 10 inches, 0 inches, and 5 inches. My analog signal. So I have a pressure transducer right here. And then at the top, I have ultrasonic. Both of those will give off a 4 to 20 milliamp signal based on the level of water. So all that's saying is the analog signal varies proportionally with the magnitude of change. So if 4 to 20 is my range, what is my milliamp reading going to be at 0 inches? 4 milliamps. What's it going to be at 10 inches? 20. All right, trickier one. What's it going to be at 5 inches?
12.
10, 12.
12. A lot of people think 20 minus 4, 16 divided by 2 is 8, but you have to re-add your 0, so 8 plus 4 is 12. So if I'm at 0 inches, it's going to show 4, 5 inches, 12, 10 inches, 20, and then everything in between. So all that's saying is that your analog signal is going to vary proportionally with whatever the process liquid is that's in this. So it'll go up and down. It should go up and down the same proportionally. Good. So that's an analog signal. Analog signal will have a span. Top right of page 29. Last 2 sentences before 410. Digital signals alternate between 2 constant values of 0 and 1. The value 0 represents off, while the value 1 represents on. So whenever you hear digital, digital, binary, discrete, all those, think of ones and zeros or on and off. Okay. Analog, you're going to have a range 4 to 20. Digital, 0 or 1. Digital, discrete, binary, anything that says that. 410 analog signals 4 to 20 milliamps and 1 to 5 volts. 410. First sentence is hot. first half of the sentence is highlighted. The 4 to 20 milliamp circuit is probably the most common electronic way to transmit an instrumentation signal from one device to another. Page 30. Y'all talked about shielded cables before. So highlight this second full sentence on page 30. Shielded cables are used to guard the low-level signals against outside interference. So shielded cables have like a cable on the outside of them that drops off electromagnetic interference. So y'all know what a BB pin or a voltage detector pin is? Like if I take it and put it on an outlet that's hot, it beeps or it turns red. Y'all know what that is? So how those work are say this is the center of a wire, or that's the end of a wire. All wires that have voltage on them or AC voltage on them output electromagnetic interference. It gets weaker and weaker the further out you go, but they all output electromagnetic interference. And as I put my BP pin there, that's when that beeps. It's sensing that electromagnetic interference. If I have a piece of instrumentation like signal wiring, and I put that somewhere right here, and I don't have any shielding on it, that electromagnetic interference is going to interfere with that signal. Because my signals are small, like 4 to 20 milliamp or 1 to 5 volt. Like those are small voltages. So if I induce a voltage on that wire, that's bad, right? Especially if I have big ass power cables, that's a lot of EMI. Does that make sense? So what you do is you put a shielding around that cable, which just looks like a metal jacket, and then you terminate it on one end, and that drops all your electromagnetic interference to the ground. So you shield instrumentation cables to prevent electromagnetic interference. Good? Second paragraph, so that big paragraph on the left, we've got 3 more highlights in that. So right in the middle, I've got a sentence highlighted. Often the receiving device will have a precision 250 ohm resistor across their input terminals, either external or internal to the unit. Often the receiving devices will have a precision 250 ohm resistor across their input terminals, either external or internal to the unit. Skip a sentence. And the next sentence is an online test question. The reason the 1 to 5 volt signal isn't simply transmitted through the loop is because the signal would be inaccurate due to the voltage drop across each device. So the reason the 1 to 5 volt signal is not simply transmitted throughout the loop is because the signal would be inaccurate due to the voltage drop across each device. Online test question. Skip another sentence. And the last sentence in that paragraph is highlighted. A characteristic of an isolated electrical circuit is that the current will be constant at every point along the circuit. Therefore, current makes a better carrier for precision signals. So we're saying this stuff is wired in series, right? If I have stuff wired in series, I have a voltage drop across each load. That's why they don't use 1 to 5 volt signals. But my current is the same at every series load. So that's why it's easier to use a 40-20 milliamp. On the right-hand side of the page, second paragraph, first sentence is highlighted. The sum of all the voltage drops across the loops must not exceed the voltage of the power supply. Remember how we did? We added up all the voltages and they added up to the voltage source. If you have required voltages at all your pieces of equipment, you have to make sure that your power supply is big enough to power everything, right?
Sorry, that was the sum.
The sum of all voltage drops around the loop must not exceed the voltage of the power supply.
Oh.
Good?
Okay. Yeah.
All right, I've still got page 31. I've got 8 highlights on page 31. So still a lot of highlights still on the page. 420, digital signals. First sentence is highlighted. A digital signal is a signal sent and received in discrete intervals rather than varying continuously over time as an analog signal does. A digital signal is a signal that is sent and received in discrete intervals rather than varying continuously over time as an analog signal does. The next sentence is highlighted as a separate highlight. These signals alternate between two fixed current or voltage levels and are usually denoted as 0 and 1. Guess what? The immediate next sentence is a separate highlight. Combinations of zeros and ones called binary numbers represent numeric values. Have y'all converted binary to decimal? I'm not gonna make y'all do that, but you know you can have, I'm not gonna get into that. You don't have to know that. I think we do that at some point in this book, if I remember right. I can't remember if it's electrical instrumentation. But you can have a multitude of digital signals and it can represent big numbers. PLCs, 430, programmable logic controllers. The sentence that splits the columns, so all the way in the bottom left of the page, that sentence down there is highlighted. The CPU makes its decisions based on the program instructions that have been loaded into its memory and sends control instructions to the output modules. So the decisions and instructions for a PLC are all done inside the CPU, or the central processing unit. 431. Way behind. 431, second sentence is highlighted. Switches and contacts are examples of discrete inputs that are connected to a PLC digital input module. Y'all ever seen a PLC before? So a PLC will look kind of like a box, like the CPU will look like that, and then you'll have boxes added to the side of it for different modules. You can have an analog, digital, for both for inputs. Then you might have one for like thermocouple, something like that. You just have different, like you can add these. It's kind of not like Legos, but kind of like Legos. Like you could just add these to your PLC rack. So for digital inputs or digital discrete inputs, you add a digital input block. So for that, you can have a switch or contacts, because a switch can only be what? Connected or disconnected. It can only be on or off. It can only be 1 or 0. Does that make sense? A contactor can only be made or not made. There's no span there. It's only made or not made. Does that make sense? So that would be for your discrete module, only on and off devices. Skip a sentence. So right after where you see binary 0 in parentheses, I have the sentence: the terms high and logic 1 are equivalent to the on condition, while the terms low and logic 0 are equivalent to the off condition. And then 432, that first sentence of 432 is highlighted. As discussed earlier, an analog input or output has a continuous signal that varies with the magnitude of the process, such as 4 to 20 milliamps or 1 to 5 volts. I'm going to skip section 4 review, and I'm just going to give that to you for homework. So I can get y'all out of here, because we got 3 pages left. Is that all right? All right, section 5. Applications of instrumentation circuitry. Temperature. 1 of the, components that you can use for temperature to measure, that you can measure temperature with is a RTD, or resistance temperature detector. My highlight for this is in the top right of page 32. Second and third sentences are highlighted. An RTD acts somewhat like an electrical transducer, converting changes in temperature to voltage signals by the measurement of resistance. The metals best suited for RTD sensors are pure, of uniform quality, stable within a given range of temperatures, and able to reproduce or to give reproducible resistance temperature readings. Everybody get that?
You started it?
An RTD acts somewhat like an electrical transducer.
You stop the readings.
Yes. I have the last paragraph on page 32 highlighted. Figure 40 shows a basic bridge circuit, which consists of 3 known resistances, R1, R2, and a variable resistor of R3. Another unknown variable, Rx, which is the RTD. You need to key in that Rx is the RTD, a source voltage, and a sensitive ammeter. So this is what an RTD bridge looks like. Page 33, second paragraph, first 2 sentences on page 33 are highlighted. Since the values of R1, R2, and R3 are known values, the only unknown value is Rx, which is your RTD. The value of Rx can be calculated for the bridge during an ammeter 0 condition. So that is, and I highlighted that equation right there. Rx equals R2 times R3 over R1. So if you're wanting to know, like if you're wanting to find out what Rx is, in the null condition, in the 0 condition of an ammeter, you would just multiply R2 times R3 and divide by R1. Excuse me. Thanks. 520. Pressure or a strain gauge bridge. First sentence of 520 is highlighted. A strain gauge measures the external force or pressure applied to a fine wire. A strain gauge measures the external force or pressure applied to a fine wire. Skip a sentence, and I have the third sentence highlighted. The pressure change causes a resistance change due to the distortion of the wire. So if you look up here on the board, all a strain gauge is a coil wire that goes through a flexible vacuum. So as you apply force to this, the resistance of these 2 wires changes. I don't know how someone figured this out one day, but they did. So you can use this for like weight scales and stuff like that. Put a strain gauge under a scale, and as you put weight on this, the resistance changes, and based on that resistance, they can tell a weight. Good. Last page, page 34. The first whole paragraph on page 34 is highlighted. Other resistance type transducers combine a bellows or a board-on tube with variable resistor as shown in figure 44. As pressure changes, the bellows will either expand or contract. This expansion and contraction causes the attached slider to move along the slide wire, increasing or decreasing the resistance, thereby indicating an increase or decrease in pressure. So all that is, you're looking up here on the board. Pressure is applied to this bellows. This thing expands. The spring counteracts that. It has a slider right here. This pretty much just works as a rheostat. So a slider that runs up and down a slide wire or a resistor. Like they can base weight on that as well. As I put pressure on this, this thing will move down, and then they can determine a weight based on how much that moves. 530 remote level indication. I've got the sentence right before the bullet points highlighted. There are 3 major reasons for using remote level indication, and then the third bullet point is highlighted. The level being measured may be in an unsafe or radioactive area. So if it's in an unsafe area or radioactive area, that's a good reason that it's remote. Somebody doesn't have to go look at the level, right?
What page is that on?
Page 34.
The level
So it's,
measure. Okay.
yeah, the sentence before the bullet points, there are 3 major reasons for using remote level indication. And then the third bullet point is highlighted. The level being measured may be in an unsafe or radioactive area.
Okay.
Next paragraph, the last sentence in the bottom left and continues on to the next page, the next side is highlighted. The differential pressure transmitter is a diaphragm with a high pressure and low pressure inputs on opposite sides. So for this picture up here, I have a differential pressure transmitter. I have the low side is going to be the atmosphere on the top, and then the high pressure side is going to be the head pressure at the bottom of the tank. So low pressure on one side, high pressure on the other side. Good. Skip a sentence, and that next sentence is an online test question. So second sentence in the top right of 34. The transducer changes this mechanical motion into an electrical signal. The transducer changes this mechanical motion into an electrical signal. Do I see that? Online test question. My last highlight is the second to last sentence on the page. Using relays, this system provides alarms on high and low level. Using relays, this system provides alarms on high and low level. You good with that? Your homework is to do section 4 review, section 5 review, and see if you can work your way through the review questions. So you've got more of those series parallel loads and stuff like that. See if y'all can have that worked out by class on Thursday. Good? All right. That is all.